Hello everyone and welcome back. Today I'm going to talk about section 3.6 in AP Calculus BC. Now this section focuses on chain rule, which is probably the most widely used differentiation rule in mathematics. I'll describe the rule and show you how to use it. Okay, so let's start out with example number 1. Example 1, and I've used this phrase, but I take all the examples out of the book, okay, so you can find these in the book and just follow along. So, example number 1 asks us to relate derivatives, and the question reads, the function y equals 6x minus 10, or they simplify it for us, how convenient. This function is a composite of the function y equals 2u and u equals 3x minus 5, okay? And the question asks, how are the derivatives of these three functions related? Alright, so let's derive the three functions right here. So this, in case any of you guys haven't gotten it yet, if you plug in u here, you get this equation, which is the same thing as this equation, right? It's just a different way of writing it. So they're asking us to take the three derivatives, okay? And so for the first derivative, we're going to take it with respect to x, okay? So the derivative here, dy, so you're differentiating y with respect to x, equals 6, okay? Let's draw that out. Next, you're going to differentiate this function. Now this is also dy, but you're deriving with respect to u, okay? So instead of dy dx, you're doing dy du, okay? And this equals 2, okay? And lastly, you're going to derive u with respect to x, because that's your variable, right? And this equals 3. And so the question reads, how are the derivatives of these three functions related? Well, let's just write everything out, okay? Oh, look. Okay, so now you're probably thinking to yourself, well, how is 6, 2, and 3 related? Okay? And you go, aha, this is what happens. If you multiply 2 and 3 together, you get 6. Well, good for you. You figured that out. But how do you get to that? Well, okay. Something that you should have learned back from your days of algebra is that if you have that you can cancel out when you're multiplying two fractions together, you can cancel out any similar terms if they're on if one's on the numerator and the other one's on the denominator, right? So you have dy dx right here, right? And you have a du here and a du here. So what do? Well, you cross them out, right? And what do you get? You get dy dx equals dy dx. Well, that makes sense because 6 equals 6, okay? And so what I'm trying to teach you here is that dy dx equals dy du times du dx. And this might look really simple, but this very generic fraction will help you ace the rest of this chapter, or the rest of this section, okay? Alright, so let's move on and do example number 2. Example number 2, again, out of the book. It says the polynomial, right here, let me shift that up a bit. So the polynomial y equals 9x to the 4th plus 6x squared plus 1, which is also equal to 3x squared plus 1 squared, is a composite of y equals u squared and u equals 3x squared plus 1. So how do you calculate the derivative? Well, we do the exact same thing as we did above. So dy dx, okay, is equal to 36x to the 3rd plus 12x, okay? And down here, we're going to derive this just continuously. So we're going to do dy du first, that's the derivative of this, times du dx, okay? And if everything goes right, then we should get the exact same, then this exact same phenomenon from up here should occur, right? So the derivative of dy with respect to du, or with respect to the variable u, is 2u, right? And the derivative of du with respect to x is equal to 6x, right? And so now you multiply these two together. Or no, sorry, excuse me. Now you don't do that. Don't do that. Okay, so now you have u here and u here, right? What do? You substitute. Okay? You substitute that in, and then you end up getting 2 times 3x squared plus 1 times 6x. And if you expand everything, it's actually not that hard. You have 12 12x here, right, and 3x squared plus 1 on the inside. If you do all that, then you end up getting the exact same thing as we got up here. So this, when simplified, equals this, okay? So now I'm going to teach you something known as the outside-inside rule, okay? Now it sometimes helps to think about the chain rule this way. So if you were to derive the function y of g of x, right? Back in Algebra 2, you used to write it fog, if I still remember correctly, right? That means plug x into g first, then plug that result into f, okay? If you were to think about the chain rule as if it were this, then the derivative dy over dx equals the f prime evaluated at g of x, the inside stays the same, times the derivative of the inside function, right? Think about it as peeling a cabbage, okay? The first layer you peel off the f, right? After you peel off the outside, the inside still remains compact, right? And then you keep on peeling until you end up into the very core. In this case, your cabbage only has 2 layers. It's a very boring cabbage, okay? So in other words, you have to differentiate the outside function f and evaluate it at the inside function g of x, right? And then you have to multiply by the derivative of the inside function, okay? You have to keep on going until you end up with the core. It was a derivative of the core function, okay? So let's do an example. Example number 4. All right. And it asks us to find the derivative of sine x squared plus x, right, with respect to x. So let's do this using this way, right? So you're peeling a cabbage. Okay. Now think about it. What's the f of x here? The f is the sine, right? You're doing sine times that bundle in the inside. So now you have to take the derivative of sine. Derivative of sine of x is cosine of x. Okay? So now you have cosine of everything on the inside. Okay? The inside stays intact. Okay? Like right up here. So you first took the derivative of sine of x, right? Sine of u, excuse me. And then you leave the inside intact. Next, you have to multiply by the derivative of the inside. So what's the derivative of the inside? Well, you have 2x, right? You move that up, so you have 2x. And x raised to the first power is this plus 1, okay? So this is your derivative. You have cosine of x squared plus x times 2x plus 1. This is what so these two are equal, okay? That's not strictly mathematical, but I'm just showing you these two are equivalent, okay? Alright, so sometimes you have to use the chain rule more than once. So it's known as the repeated use of the chain rule, nothing creative there. So we sometimes use the chain rule two or more times to find a derivative. So here's an example. This is example 5, so I'm just going in order this time, okay? We're asked to find the derivative of g of t, right? If g of t equals the tangent of 5 minus sine of 2t, okay? So we're going to do this, right? Only this time you can count how many okay, I'm just gonna let you guys think of the answer right now. How many layers are there? Okay, think of a number. All right, if you answer 3, then you are correct. Okay, now many of you may have counted 2. Okay, and that's that's understandable, but I'll show you why that is wrong. Okay, so let's start by peeling the outside layer, tangent. Okay, so let's start here. Okay, so we're asked to find g prime, okay? Now we have to first take the derivative of tangent. Now, if you guys don't remember, dt of tangent t equals secant squared t, okay? So now we have secant squared, and we keep the inside intact, right? Inside doesn't change. Now we have to multiply by the derivative of the inside. Okay, the inside function. Now we're going to take the derivative of 5 minus sine 2t. Okay, now 5 disappears. Okay, 5 because it's a constant. Remember, the derivative of a constant is always 0. Okay, so 5 disappears, 0. Right, and then you have negative sine. So treat the inside as x. Okay, treat the inside of x as x. So sine of x goes to cosine of x. So negative sine of x goes to negative cosine of x. Okay, so you have to multiply this by negative cosine of x, or cosine of 2t, sorry, the x is 2t, and I just did that, and you'll see why I did that, okay? And next, you have 2t right here. This is a function in and of itself, okay? 2t might not, it's really obscure, but you have to pay attention to the details, okay? So the more obscure functions are the ones that usually make you lose points on the tests. So always make sure that you are completely just out of functions. So now you have to derive, or you have to find the derivative of 2t, right? And this, of course, just equals 2, okay? So you multiply by 2. And this is your derivative, all right? This is your derivative right here for g of t. Now the next example, example number 6, the one that follows this, deals with parametric equations. I'm not going to go into great detail on that because you're going to cover it in chapter 10, and that's going to come nearly 6 months after chapter 3. So just hold your horses on that. All right. All right. So once again, I'm going to end today with a multi-step 2-part equation. Okay. I love word questions, and they're especially helpful with understanding concepts as a whole, and it just feels good to be able to apply everything that you've learned. Okay. So this is example number 7. Right, example number 7 is finding slope. So part A asks us to find the slope, right? A says find slope of the line tangent to the curve y equals sine x raised to the 5th power at the point where x equals pi over 3, right? So now you're going to have to derive this function first. The first thing you have to do, derive, okay? This is chain rule. If y equals sine x raised to the 5th, then dy dx, okay, equals 5 sine x to the 4th, right? Okay, you got to move that up. This is power rule, right? You have to multiply it by the derivative of the inside. So what's sine of x? Or the derivative of sine of x? And that, of course, is cosine of x. Okay, so this is your derivative of the function y. Alright, and so the tangent has a slope, so now you're going to evaluate dy dx at x equals pi over 3. And you're going to plug that into here. Okay, so you're going to do 5 times... So put everything in parentheses, it's much easier to manipulate once you get that working, right? And then you have to multiply by cosine of pi over 3. This is back to unit circles, alright? Don't make it haunt you. Go look at it tonight before you go to sleep. Okay, so sine at pi over 3 is root 3 over 2, right? And then you have cosine at pi over 3, right? That's 1/2. These two come together. Other way, okay? And so once you evaluate everything, then you get 45 over 32. This is your slope, okay? Slope at x equals pi over 3. Alright? That's your slope. So part B now asks us to find the slope, or show, right? Show that the slope of every tangent line to the curve y equals 1 over 1 minus 2x, all of that cubed, is positive. Okay? And what we're going to do here is we're going to once again take the derivative of y, right? So dy dx equals ddx of 1 minus 2x raised to the negative 3rd, right? So you move, so this is negative 3 raised to the 1 minus 2x raised to the negative 4th times the derivative of the inside, which is basically negative 2, right? Negative 2 right there. And so once you get, so now you're going to solve, so now you're going to expand this, right? This becomes 6, right? So this is equal to 6 over 1 minus 2x raised to the 4th, okay? Now, so how are we going to show that the slope of every tangent line to the curve to this function is positive? Well, at any point x, y on the curve where x doesn't equal 1/2, right, that would make it 0. But at any other point that in which x does not equal 1/2, then the slope of the tangent line is the quotient of two positive numbers, right? You have 6, that's a positive number, and any number raised to the fourth is a positive number. So when you have the quotient of two positive numbers, then of course you get a positive number, right? And that is how you show that the slope of every tangent line to the curve y equals 1 over 1 minus 2x, all of that raised to the third, is positive.